My name is Peiqing Chen. I am from Peking University, and I am a senior undergraduate student. Today, I'm going to present my paper, whose title is Out of Many We Are One, Measuring Item Batch with Clock Sketch. Item batch pattern is based on this data stream model, where each item has its ID, which is duplicatable, and each item passes a node at different time. As the animation shows, when the data stream flows, each item passes the node. Here, we give a brief definition of what item batch is. A batch is formed by items with the same ID. Adjacent items in the same batch are closer than that in distinct batches with the same ID. Item batch pattern can be generated by various reasons, both by machine actions and human user behaviors. For example, TCP protocol generates a batch of packets within one RTT window, and all these batches, they may converge at certain nodes, they may entangle with each other and form a data stream. And what we are going to do is to mine this item batch pattern from the data stream. Given time window t, we denote that each two items with the same ID belongs to an item batch as long as their time interval is less than t. In this animation, items with the same color defines that they have the same ID. Here we see that the 4 green items, they form item batch B1. The following 6 yellow items, they form item batch B2. The next 5 blue items, they form item batch B3. And lastly, the 5 green items, they form item batch B4. Or in a word, there are 4 item batches in this data stream. This paper is the first to observe and generalize item batch pattern from various data stream applications. We observe that item batch is ubiquitous in cache stream, per-flow burst detection, advanced persistent threats detection. Let's see to the first case of cache stream. Here, each item with the same color denotes as key-value pairs with the same key, which means that it points to the same address. We would like to generate as much cache hit as possible. So, before a batch of memory fetching requests with the same key arrives, we would like to prefetch it into the cache and then generate a bunch of cache hits, just like the blue item shows. And when the group of memory fetching requests ends, we would like to evict it from the cache so as to leave space for later items. In this story, each memory fetching request group is an item batch. Let's see to case 2, per-flow burst detection. It is a vital problem because we would like to know which flow is causing the burst. It is vital in congestion control and suspicious flow detection. As the animation shows, at first, the flow of yellow and white items come at a constant but low speed, and all in a sudden, the yellow boxes come at a very high speed, causing a dense pattern in the data stream. And such dense pattern is most likely to be a burst. And then we can define burst as dense item batch. The third case is APT detection, also known as advanced persistent threat. It may be generated by somebody is going to implement a worm virus into your computer in order not to get detected by the firewall. For example, it sends a packet twice a week with rather low frequency. It is rather hard to be detected. And this is just converse of burst pattern. APT is sparse item batch, which features in large timestamp but small number of items contained. And now we give 4 tasks of item batch measurement. The first task is item batch activeness. It means if there exists an item of an item batch within the time window t, then we call the item batch active. For example, at this current time, there are yellow and green items within time window T, so we call item batch B1 and B2 to be active. At this time, there are blue and yellow items within time window T, and item batch B1 has gone inactive. And finally, at this time, only item batch B4 is active, or item batch B1, 2, 3 have gone inactive. The second task is item batch cardinality. It means the number of different item batches. It is highly correlated with the first task. For example, at this current time, B1 and B2 are active item batches. Thus, the cardinality is 2. At this time, item batches that are active are B2 and B3. The cardinality is still 2. And at this final moment, the cardinality is 1 because only B4 is active. Item batch cardinality measurement is vital, for example, in cache policy. Maybe there are many concurrent memory fetching request groups, and we always like to pick the most significant ones and to put them into cache so as to generate as more cache hits as possible. Thus, we have to conduct cardinality measurement to pick the most significant ones if the number of concurrent memory fetching request group exceeds the capacity of the cache. The third task is item batch time span. It means the time interval between the first and last item in an item batch. For example, at current time T0, the first item of B1 arrives. And at current time T1, the last item of item batch B1 arrives. Thus, B1 has time span T1 minus T0. The fourth task is item batch size, which means the number of items in an item batch. We see from this animation, item batch B3 has 5 items, thus the size is 5. The combination of item batch timestamp and size measurement is important for example, burst detection and APT detection, because when we do the division of item batch size and time span, we can compute the density of item batch and deduce that it is more likely to be a burst or an APT. Unfortunately, existing solutions can only solve 1 or 2 among all these 4 tasks. In this paper, we propose clock sketch, which can solve all of them at a time. The design goal is to design data structures to real-time monitor item batch information and support lookups in full measurement, because real-time information is always more important, for example, in burst detection. And the key ideas are, first, to use Sketch to record active item batch information. The second is to use clock to clean outdated item batch information. This page shows us a clock sketch framework. It is combined of 2 parts. The first is sketch cells. The second part is clock cells. And one sketch cell corresponds to one clock cell, which forms a pair. Each clock cell is 1 bit. And when inserting an item E into the sketch cells, it picks several hashed locations. For example, in this animation, we show 3 of them. And the information of item E is stored into these sketch cells. Also, correspondingly, the 3 corresponding clock cells are flipped into 1. In order to do updates in the clock cells, there is an extra thread which cleans the clock cell T at a time circularly. And in the next few pages, I will show you cases about how the clock cell works. Let me show you the example of using CountBin Sketch plus clock. CountBin Sketch, also known as CM Sketch, is a data structure used to conduct frequency counting. When inserting an item E, it picks several hashed cells. And in this example, we give 3 of them. And it adds 1 to all these 3 cells. For query, it picks the minimum value among all these hashed cells, which is 1 in this case, as the frequency estimation. After inserting into the sketch cells, the corresponding clock cells are flipped into 1. And when the clock hand traverses a pair of cells whose clock cell is 1, it preserves the sketch cell value and it cleans the clock cell into 0. And when the clock hand traverses a pair whose clock cell is 0, it resets the sketch cell into 0. And when it traverses a pair of 0, 0, the clock hand simply does nothing. The rationale behind is that a counting sketch is suited for size counting, and clock can do elimination of inactive item batch counting. Thus, a combination of them can conduct item batch size measurements because inactive item batch size are eliminated by the clock. Also, clock can work with the Bloom filter, which is a probabilistic data structure to conduct membership query. Same as counting sketch, it uses several hashed cells and flip the cells into 1. And all these sketch cells of Bloom filter are bits. They can be either 1 or 0. After flipping the Bloom filter bits to 1 and the clock cells also to 1, the clock hand traverses a 1-1 pair and it preserves the Bloom filter bit but cleans the clock cell. And when it traverses a pair where the clock cell is 0, it resets the sketch cell, which is the Bloom filter bit, to 0. And also, when it traverses a 0-0 pair, it simply does nothing. The rationale behind is also similar. Bloom filter is suitable for membership query, and clock can do elimination of inactive item batch membership. Thus, a combination of them can do item batch activeness measurement. In this paper, we propose clock sketch, which is a combination of clock and quality sketch, which means a batch of probabilistic data structure. We put forward 4 clock sketch algorithms to respectively to item batch activeness, cardinality, time span, and size measurements. Due to space limitation, in this video, we only talk about 2 of them. For the rest of them, please refer to our paper. However, directly using clock can't reach highest measurement accuracy because clock has error in cleaning outdated information. It is not 100% accurate, and it has an error window behind, which I will illustrate later. Basically, using 1-bit basic clock has 2 large error windows, which means preserving too many outdated item in batch information. In this page, I will show how multi-bit clock will affect the size of error window. This part shows how using 1-bit clock cell, all items will be preserved in the data structure within 1 cycle of clock hand traversal, which is the green part denoted as a standard window. And item information will be cleaned beyond 2 cycles of clock hand traversal, which is this part, and thus generating an error window between T and 2T. This is known as the error window, which is the blue part. Items within this window, they are outdated information, but there's probability that they are wrongly preserved in the data structure. Let's see what will happen if we use 2-bit clock. All records are preserved within 3 cycles, where this time, the traversing time of the clock is T/3, 3 times faster than using the 1-bit clock. And all information will be cleaned beyond 4 cycles, thus generating an error window of 1/3 of T, which is 1/3 of the error window using 1 clock cell. If we go further into using S bits, the error window shall be T/2 to the power of S-1, which is far smaller than using 1 or 2 bits. Thus, we see that using more bits of clock cell can generate an even smaller error window. thus preserving less outdated information in the data structure. However, there is a limit because we always have fixed memory to do measurement and want to get the highest measurement precision. If we use a larger clock cell size, the pros is that we can have smaller error window and have less inactive information preserved thus. However, there is trade-off because each clock cell is larger and the pair of sketch cell and clock cell takes more space. Thus, there will be less sketch cells, which will cause a higher hash collision probability, which will increase the measurement error. Thus, there is an optimal clock cell size. And in this paper, we give concrete mathematical analysis on how to choose the optimal clock cell size based on experimental parameters. For example, the data stream pattern and the memory restrictions. Finally, let's see to the experimental results. The setup is using C simulator to write the clock sketch algorithm, and we use 3 real-world data traces. The first one is KIDA, is an anonymous IP trace. The second one is Criteo, which was a machine learning-based data trace with timestamps. The second one is Network, which is a real-time monitoring of Stanford campus network. And the first experiment is on topic of choosing optimal clock cell size. The task is to conduct item batch size measurement. The metric is average relative error. It means the average relative error in measuring the size of each item batch. And when we are using smaller memory, give it 16 kilobytes. We show that from the graph, the point reaching lowest ARE is 3 bits. And if the memory is enlarged to 64 kilobytes, the optimal clock cell size is 8 bits. And the reason of this is as follows. When the memory is more restricted and small, the hash collision effect is more serious. Thus, we have to generate more cells to avoid hash collisions. Thus, we can only have smaller clock cells. And when memory was enlarged, we can have more space to give larger clock cells to eliminate more outdated information from the data structure. This page is the experimental results of clock sketch accuracy measurement versus the state of the art, and the metric is false positive rate, and the task is item batch activeness. False positive rate means the number of truly reported item batch activeness over the total number of queries conducted. We see that when using memory, for example, as 2 to the power of 7 kilobytes, our algorithm can do 10,000 times more accurate than the state of the art. And the rationale is like this. Using more memory efficient data structure of clock to clean outdated information, rather than using timestamps, which are quite big, usually 64 bits, is the key behind this. We are more memory efficient. And thus, it shows clock sketch outperforms the state of the art when memory is especially limited. So let me wrap up. This is the first work to observe item batch pattern from various data stream applications. And we designed clock sketch to comprehensively measure item batch. As for future work, there are 3 aspects that we can go. The first one is to study item batch formed by similar items rather than identical ones. The second is study self-adjusting threshold T rather than given and fixed threshold T at first. And also, T may vary from time to time for the same item batch. Number 3, distributed measurement rather than single node measure. Our code is open source on GitHub, and this is all I want to deliver today. Thank you for your time.